negative 20 kilojoules per mole. Delta Cp is given as 0, which is just another way of saying that the heat capacity of A is equal to the heat capacity of B. And those heat capacities and then finally we're given that the equilibrium constant is 10 to the 5th at 298 Kelvin. We have a pure A feed. And it's feeding at a temperature of 300 Kelvin. And we're asked to find the equilibrium conversion and temperature.
Is this a adiabatic reactor?
Yes. All right, so last time we derived an equation for the equilibrium conversion as a function of the equilibrium constant. It's not gonna work. Everybody remember that? And so now what is Kc? So what's Kc equal to? Yep. Right. So are you given Kc? At a temperature. Can I just plug that in? Yeah, so in a manner of speaking, yes. The other thing you have to remember is that what temperature do we need it? So we have it, it was, I think, 10 to the 5th at 298, right? No?
Yeah, there's two of us, right?
298. Do we want it at T naught? No, right? That's not useful to us either. Okay. So from the Van Hoff equation, we know that the equilibrium constant at some temperature is equal to the equilibrium constant at some other temperature. And this is where you can get confused from all the different T1s and T2s and stuff. So I'll just put in the temperature directly. do we have any other relationships that we can use?
Yeah, for our design equation, for the temperature, the equation we just got on the board.
Yeah, so let's put up the energy balance and see if that helps us. Temperature, that one I have. Okay, so this gives us temperature as a function of conversion. Is that helpful? Is there another one that we had? Can we rearrange that to give us something, another formula?
We can do x equal to
So X from energy balance is what you normally see here. Alright, so does that help us? Do we have everything we need in order to solve that equation? So we have two equations, one for Kc, right? And I can substitute this in to here. And then I have an equation for the equilibrium conversion as a function of what's left in here. Temperature, and nothing else. And then I have this equation that's the energy balance conversion as a function of what's over here that I don't know. Temperature. When I'm at equilibrium, are those two things equal to each other? Yeah, right? That's the whole idea. It's the intersection of those two lines. The two lines, the straight line, that's XEB. And this is X equilibrium. So when those two are equal, then we're happy. So yeah, you can set them equal to each other and solve for t, and that's what we're going to do. But this is the better form to start with, not this one. This one is not as useful. And that's simply because this equation is written out as x is equal to some function of temperature. So we want to use the same form of equation when we're dealing with the energy balance. X is a function of temperature, and that way we can just set the two x's to each other and solve. All right, so let's put in what we know over here. This simplifies. Is anything 0 over here? Right, so this goes away. This whole term goes away. And what do we have here? What's theta? What's the sum of thetas? 1, right? It's just theta A is 1. So the heat capacity of A times this temperature difference. And we only have, all the inlet temperatures are the same. Well, there's only one species coming in, so I don't need the Ti. I can just put T0. Divided by that's it. Right? And so if we put numbers in, what was CPA? 50, I believe. This is still T, still unknown. T0 is 300. And this is 20,000, right? If we're keeping the units constant. And so you end up with so at this point, this is no longer x simply EB, but that is x equilibrium, right? Because the only way that I can, okay, now it is. Because I'm saying that that's true at, when this temperature is also at equilibrium. Okay, so that's one of our formulas, and then so we can say so this is equal to from here, so 10 to the 5th.
Can I read that?
He's done some math here. That's okay.